When we have a particular target for synthesis, we're inherently limited by the reactions that we know. Now, once you progress through organic chemistry, if you were to do organic chemistry research, we would, of course, look in literature for those reactions. But what you're really limited to thus far in your organic chemistry journey is the reactions we've learned. So, for example, we've really only learned 2 reactions in Chapter 9 that produce an ether. And so these sections are talking about how can we produce ethers. And so we've learned 2 reactions. These are entries 4 and 5 in Table 911, which is also Figure 10.3. And so when we decide to synthesize an ether here, we have to ask ourselves which reaction would be the best one to synthesize an ether. For some ethers, we could devise a practical synthesis using either of these reactions. For example, this equation here shows 1 butoxybutane can be produced using kind of that first reaction in the previous slide by treating 1 bromobutane with sodium 1-butoxide, right? So we're using what we call a deprotonated alcohol for this. Now, this type of reaction has a really specific name. It's called the Williamson ether synthesis. It's named after Alexander Williamson, who lived from 1824 to 1904, right? And so he was an English chemist that developed this reaction. And in the Williamson ether synthesis, what we see happening here is an ether is produced by reacting an alkyl halide, right, with the salt of an alkoxide anion, okay? The alkoxide salt dissolves in solution to just form the alkoxide anion, and that's a strong nucleophile. And so if we were to look at the mechanism here, right, what we would see is that the electrons on the oxygen come and attack the carbon that the leaving group is attached to, okay? This, through a backside attack, this is an SN2 reaction, right? And then these electrons go on the bromine, and what we see form then is the 2 groups remaining. So 1, 2, 3 from the alkyl halide. We put the oxygen there, and then let's see. Oh, I've left something out, I think. Hold on. Oh, yeah. I left out a carbon. There. The oxygen goes there. I was like, always go back and double check, which is what I was doing. I just wasn't saying it because I was going 1, 2, 3, 4, 1, 2, 3, 4. And when I got there, I only had 3 carbons. And so it's really, you always want to kind of double check your carbons to kind of check your work. And so now I've got 1, 2, 3, 4. And so I look here and I have 1, 2, 3, 4. And then I look here and I have 1, 2, 3, 4. So you're not, in this synthesis, right, you need to count the carbons here and count the carbons here and make sure they add up here, okay? So notice, so this is the mechanism for the Williamson ether synthesis. I do have a picture of the fine fellow right there. Now, we can produce the same ether using the second reaction that was shown in the previous figure, where we heat this up in the presence of an acid. You can use sulfuric acid or phosphoric acid. This is called a condensation reaction. And basically what happens here is 2 molecules of the alcohol are joined together and a molecule of water is lost. So in a condensation reaction, This is a really broad umbrella term for a lot of different reactions, but it's basically what happens when you have two larger molecules that are joined at the expense of the loss of a small molecule. Now, a lot of times this is water, but it doesn't have to be, right? But in this case, like I think a condensation and then condensation on the outside of a bottle and it loses water, and then it's condensation and we're losing water there. So again, it doesn't always have to be that. Just kind of as a fun side note, you'll notice that we've got butane 1-ol here. And you'll notice on the start of chapter 10, I had some pictures of ice cream. The natural fermentation process of sugars will produce butane 1-ol in small amounts. And so it's used as a flavoring agent in a variety of food and beverages, including ice cream. So I thought, what better way to kind of start the chapter than with some pictures of ice cream. All right, so let's look at the mechanism for this condensation reaction. When we look at this, we are going to start with our 1-butanol, okay, and our sulfuric acid. Now I'm going to draw the sulfuric acid like this, because it helps just facilitate the reaction. And the very first thing we're going to see is a proton transfer reaction. Now, when you draw mechanisms, you need to draw in your electrons. And so the electrons on the alcohol are going to come and steal the proton here. And these electrons that make up the bond between the proton and the oxygen are going to go back on that oxygen. And so we have a proton transfer. Okay. Now we're going to follow our arrows to see what we formed. We've got an O and H. That second H had been added. We have 2 electrons and we have a positive charge. Now, water is a really, really great leaving group. So what happens is a second molecule of 1-butanol, or butane 1-ol, comes in and will attack the carbon next to the leaving group, and then that water is bumped off. So that water's lost, and this is an SN2 reaction. So then 1, 2, 3, 4, oxygen, 1, 2, 3, 4. There's a hydrogen there, and that means this has a positive charge. Don't forget your positive charges, okay? And so we have another proton transfer to remove the positive charge. Right? These electrons come here and steal that proton. Those electrons go back on the oxygen. Right? And now we have our ether, and then we produced H3O plus, right? And that makes sense to us because this is an acid and our product here is also an acid as well, right? So the mechanism here proceeds by an SN2 step because the leaving group is on a primary carbon. Even though the conditions of the reaction tend to favor an SN1, a weak nucleophile, excellent leaving group, protic solvent, SN1 reactions are unfeasible with primary substrates. So the primary carbocation that would be formed would just be too unstable. So when the alcohol is secondary or tertiary, SN1 reactions become more likely. So, but this proceeds through an SN2 reaction. Now, we've got 2 ways to synthesize ethers. We've looked at the 2 mechanisms. Let's look at synthesis of other types of ethers. So let's say that we want to synthesize this big boy right here. This is isopropyl ether, or 1,1-methyl ethoxypropane. And what we find is that the synthesis of other ethers can really be subject to severe limitations that make one method of synthesis a lot more feasible than another method. So one of the things to be aware of is this is an asymmetric ether. An asymmetric ether just means, right, that this group and this group are different. So this is asymmetric. Ooh, let me make sure. Always never know if it's two S's or two M's. There we go. It's asymmetric. We can envision carrying this out through a condensation reaction, but it's not really a great choice because in a condensation reaction, you have two alcohols that react together, those two functional groups. So to make an asymmetric or an unsymmetric ether, you would need to add two alcohols here, and the desired product would be these two alcohols reacting together to form this. But what you would have is a lot of also undesired products, right? You would have this guy reacting with this and this guy reacting with himself, and you would get these. And so that means to get the desired product, you'd have to use a lot more of your reactants, which are expensive, and you'd also have to come up with a separations method to separate all three of these. So it's just not a really great method condensation just isn't a really great method to synthesize things that are asymmetric. So we can kind of use a broad sweeping generalization where condensation reactions are typically feasible for synthesizing symmetric ethers, but unfeasible sorry about the doorbell there. But often unfeasible for synthesizing an unsymmetric ether. Okay, so symmetric ethers, condensation reactions are good methods. Asymmetric ethers, they're not so great. Okay, so one of the things that's really helpful about the Williamson synthesis is that both symmetric and unsymmetric or asymmetric ethers can be produced. And so when we look at this example in 1017, this shows how a Williamson ether synthesis can be used to produce the 1,1-methyl-ethoxypropane, right? Only one ether is produced rather than that mixture of ethers because only one alkoxy anion here can act as a substrate. So this is honestly the best way, definitely the best way to produce unsymmetric ethers, but you can also produce symmetric ethers if these two groups were the same group, okay? Now, that doesn't mean that Williamson ether synthesis can be used in every situation. There are limitations to the Williamson ether synthesis. One of those limitations is shown here. So you need to remember that this proceeds through an SN2 reaction. And so that's going to have the same limitations of any SN2 reaction, most notably that we are going to have an issue of steric hindrance. Right? So SN2 reactions are unfeasible for tertiary substrates. That's a tertiary substrate. Right? So in this reaction, the sodium ethoxide basically doesn't go through an SN2 reaction at all. It will go through an E2 reaction. So what we find is that in some of these cases, like for example, the Williamson ether synthesis would work for a lot of cases, but not all of them. And so maybe we would use condensation in this particular instance. So a lot of trying to figure out how to synthesize products is figuring out what the best recipe is, right? And making sure that you don't fall into any what we call synthetic traps, which we'll talk about later, but things that could sabotage your synthesis, right? Or make it not as fiscally possible. So let's do an example. Devise a William ether synthesis that would produce the ether shown here, which is the intended ether product in equation 1018. Okay, so when we look at this, we need to ask ourselves some questions. We need to, ask ourselves, why was the Williamson ether synthesis in equation 1018 unfeasible? The reason is that the substrate was tertiary, right? So that substrate was tertiary, and so steric hindrance prevented the nucleophile from attacking. And so the question that you need to ask yourself is, could there be a different combination of alkyl halide and alkoxide anion to produce the same ether? So a Williamson ether synthesis requires an alkyl halide as the substrate and an alkoxide anion as the nucleophile. And we need to kind of put two pieces together, right? We need to put this piece together and we need to put this piece together. So the other combination that we could use would be to just switch those to where the ethyl substituent, and it's not a substituent, but the ethyl group there would be on your alkyl halide, and then that T-butyl group would be on the alkoxide. Right? And so this would then combine to form that molecule. So you need to also ask yourself, is this feasible for an SN2 reaction? We're using a primary substrate, right, that have very little steric hindrance, so they tend to favor SN2 reactions. And so because we can trade this around so that we would use a primary substrate, this would be one option that we could use to synthesize the reaction. So this is not where I expected the screencast to end. I have a couple more slides talking about ethers, but apparently they did not carry on over. So this is not going to be quite as a clean break as I would like. So just go ahead and start the next screencast, and we'll finish up with ethers and then talk about converting alcohols into alkyl halides.